So let me get started. Welcome everyone on this third BUILDCHAIN webinar. We are very happy to have all of you here. First, let me start with a short introduction for those of you who were not here at the previous webinars. So this is a webinar series of the BUILDCHAIN project, and I would like to ask Milena to post the website of the BUILDCHAIN project so that you can learn more about it. On our website, you also find our social platforms, and on the social platforms, you can find links to the earlier webinars. Our first webinar was an introduction to the BUILDCHAIN project in general. Also, you could learn about what is a knowledge asset and how we make this decentralized knowledge graph of origin trail helpful to make an ecosystem around the building sector. You also saw a presentation on the first webinar about what was the third topic. It was an example how to build a digital logbook, how to make a platform around all this digital information. And on the second webinar, we already started with the ideas of economics, business models, sustainability. And this is the second part of the webinar. So in the previous webinar, you heard what is a 3D BIM, building information model, how it can be used for more efficient design, what is a 3 and 4 and 5D BIM, how it can be extended with more and more digital information, and how you can turn it to be really useful in the design process and in also further processes for building. Okay, so let's get started with today's topic. It's mainly about energy efficiency, sustainability, and management still. We will have 3 webinar talks, and I first welcome George. Hello, George. So let me introduce you to the audience. Professor George Stamoulis works at the Department of Informatics at the Athens University of Economics and Business. He is the head of a big research group. He made his master's and PhD at MIT, but he has an electrical engineering background, which I just learned now that I had to read your profile, George. So his main research interest is economic and business models for networks, clouds, smart energy grids, blockchain environment, and so on. He has a very strong profile on these topics and collaborates in many big European projects. And I'm really happy to have you on board, George, and yours is the floor.
Okay, thank you very much, Noemi, for this very flattering introduction. I will share my screen now. So I'm going to present our main issues about economic mechanisms for demand response and energy efficiency, which is a topic very relevant and one of the key issues to be addressed by our project BUILDCHAIN. And this is joint work with my colleagues Thanasis Papaioannou and Dr. Marlena Minu, who were both members of our team. So the main issues to be addressed in my talk will be introduction to economic mechanisms, and then I'm going to introduce demand response and energy efficiency in smart energy grids. Then I'm going to address how users can be incentivized to participate in such DR and energy efficiency events, and also discuss about both economic and non-economic incentives. And then I will briefly outline the relevance of these issues to BUILDCHAIN and how we can address them during our project. So I will start with another example of a complex digital ecosystem, namely the internet, which is very familiar to all of us. So in the internet, we can see today many different players which act simultaneously. Of course, we have ourselves, who are the customers and the users, and we have a multitude of providers, namely content providers, over-the-top providers like Google, cloud providers hosting applications and data, network operators, and so on. So all of these players are self-interested, and they have to collaborate in order for the provision of an end-to-end service. So, for example, if I subscribe to a service where I get, let's say, the update of stock market news in my email or in my mobile, then there are at least uh, content providers who have this information and collaborating with hosting providers of hosting service for the application, and also with network providers. So all these have to complement each other in order for the service to be provided to the end user. They have their own roles and functionalities, but at the same time, although they act complementarily, they have a conflict in interest, because in this value chain they will have to share among them the income, the price that I pay for this service. So this, in some cases, is referred to as a tussle in the value chain. That is the fact that although these providers coexist and interoperate, at the same time they are engaged into economic conflicts. So conventional optimization problems used to aim at achieving a global optimum for some criterion, a single criterion, possibly combining metrics of interest to multiple providers, and at the same time they would assume that there were a central entity possessing often full information for solving this complex global optimization problem. However, such a formulation is not suitable under the tassels, because each player has his own interest, and we cannot assume that if we have the solution of this global optimization problem, that it will be adopted by the players. So because the adoption of such a solution cannot be imposed. So we have a new objective, which is reach win-win situations. That is, solve the optimization problem in a distributed way, and reach an equilibrium operating point where everybody will be happy, and take into account the decisions and the interests of each individual player, who of course will be pursuing its own interests, the distribution of information and functionality among them, the protocols and the technologies already established, and also, in certain cases, the very large scale of the ecosystem. So although I started an analogy with an analogy of internet, this analogy also applies, this approach, I'm sorry, also applies to to other complex value chains, like, for example, the smart energy grids, where we have, let's say, providers, DSOs, TSOs, end users, aggregators, retailers, all of them forming value chains and complementing each other, but at the same time being engaged into such tussles. So in year 2007, the Nobel Prize of Economic Sciences was awarded to Myerson, Maskin, and Hurwitz for their contribution to mechanism design. So, and Myerson said that incentive constraints should be considered co-equally with resource constraints in the formulation of economic problems, while Maskin mentioned that mechanisms can help us attain an efficient outcome in a complicated optimization problem in a distributed way. And in some sense, this is the engineering side of economic theory. some people refer to mechanism design as reverse game theory. So that is when we know the rules of a game, we have to find what the outcome will be. In mechanisms, we know what the outcome we want is, and we are looking for the rules of the game. I will now show you a successful mechanism, which of course is in an everyday context. And this is the mechanism we have in certain supermarkets, where in order to use a card, we have to insert a coin. And so this indeed is a win-win situation, and it is incentive compatible, as we also say in economics, because if I want to take my coin back, then I have to fetch the card back to its original position. And so by this way, the problem, unquote, of managing the cards and putting them in the right position is solved in a distributed way. Of course, I may be in a hurry and decide on my own not to take my coin back and leave the card next to my car. In this case, I will lose the coin, but I will win, let's say, a few minutes, which may be valuable for me. At the same time, the coin will be will be used by the provider in order to cover the cost of bringing the card back on his own. So, in the Services, Technologies, and Economic group of AUEB, what we do exactly is that we investigate, develop, and apply concepts and mechanisms of in the areas where ICT technology, economics, and information distribution meet. So we, as Noemi already said, we are engineers and informatics, computer scientists, computer scientists, but at the same time we employ these basic economic concepts and business modeling in smart energy grids, of course, future internet and blockchain, electronic markets, telecoms 5G, and in other areas as well. Because our main, let's say, theme is that we cannot impose an optimal solution, but we have to make sure that the right incentives are in place in order for each of the players to adopt their own optimal solution. And at the same time, this adoption by each of the players will lead to a good situation, to a beneficial situation for the whole society of players, including, of course, us, the users. Now, we'll go back to smart energy grids and look at the concept of demand response, which is the request by the provider for reduction of consumption. In this figure here, we see a case where a peak is expected at some during some time zone, and of course, the provider asks for the consumers to reduce their consumption at this time zone in order to avoid this peak. And what will the benefits be if this is indeed attained? We will have reduced outages of the system and increase reliability. We will have a balanced system, so the system will be balanced and the transmission network will have less risk of an outage. We will have, of course, some savings for the consumers, and we will come back to this because consumers will consume less. The market will overall operate in an improved manner. We avoid the use of costly power generator units, which also often are not environmentally friendly. So in this way, we also have environmental benefits and reduced CO2 emissions. So here also we see another figure, which shows another economic benefit of a successful demand response event, that is that the price of the wholesale market, which would have been this one if the consumption, the demand would have been this high, will drop to a lower level, and this is beneficial in an economic manner because the demand will be reduced at this level due to this behavior and to the successful participation of certain consumers to the demand response event. These benefits mostly apply also to a successful induction of energy efficient behavior, like for example, do not have an open window at the same time, have electric heating operating during the winter, or shutting down the computer in case no, I will be away from my screen for half an hour or more. So, and we can also name several other energy efficient behaviors, which do contribute slightly, each of them, but at the same time, if we take into account the large scale of the system, we can attain a considerable economic and at the same time environmental benefit. But in order to make sure that a DR event will be successful, we have to first think about how users choose their optimal consumption schedules. So users will, let's say, a perfectly informed user will decide on how much energy to consume for each of his appliances and for each time unit. And in order to strike the best possible balance between two counteracting factors. One is the utility, that is the comfort enjoyed by the user due to consumption of the consumption schedule, and also the fact that the user has to pay for this consumption. So economists formulate this problem, this optimization problem, by introducing the metric of net benefit, which is a combined metric, namely is the difference between the utility expressed in monetary units and the payment due to the consumption. Of course, if I consume more, I will have a better comfort, but I will pay more. So if I consume less, I will have a discomfort, but I will pay less. So we have to find the optimal point, and this optimal point corresponds to the optimal schedule of energy consumption for each user. So in DR events, in DR events, we have to modify the optimal schedule. So how can optimal consumption schedule be modified? For a particular pricing scheme faced by the user, the optimal schedule is given. So we have to change, one way is to change the pricing scheme. And so we have price-based demand response mechanisms to which the user reacts to modified price signals. For example, we can have critical peak pricing where, let's say, if we are in the summer in Greece and let's say we are expecting 40 degrees of temperature, then the retail price is increased in order for users to reduce their consumption of air conditions. So this is one way. Another way to modify the optimal consumption schedule of a user is to provide to him incentives. So we have also incentive-based DR mechanisms. And the idea is here that although the pricing scheme does not change, the user agrees to reduce her consumption when being offered adequate economic incentives. For example, we can ask for a user to reduce his consumption of air condition in case of a very high temperature, because an outage, there's a risk of an outage, and at the same time give him a discount or let's say another kind of rebate. This is the scheme of critical peak rebate. Okay, but we have another important question to address here. What is the optimal amount, monetary amount for the user incentives? Because the user, when he lowers his total consumption, will suffer a loss of utility because he will experience a discomfort. Of course, at the same time, the user will enjoy savings in his bill because he will consume less energy, but overall he has a lower net benefit. And this is, how are we sure that the net benefit is lower? Because we assume that before asking the user to participate in the R event, he had chosen the optimal schedule for energy consumption. So now the net benefit is lower, and the only way for the user to accept to participate in the DR event is for the provider, which can be either, let's say, the retailer or the DR aggregator. So I will use the term provider, let's say, in a more general meaning, to provide such monetary incentives so to maintain the original value of net benefit, which was the optimal one. So, and thus the incentives have to be offered should be at least equal to the loss of net benefit by the user due to this lower consumption, let's say, of the air conditioning. And this equals to the loss of utility due to discomfort minus the bill savings. So the user should not just be compensated for the discomfort, but slightly less, because he will also have an economic saving due to consuming less energy.
Sorry, George, just let me break for a few seconds your talk. You have 5 more minutes,
Yes,
by the way.
right.
And also, I forgot to say the audience that they have the possibility to post questions in the questions and answers chat window. And we will answer the questions, or the talkers, the presenters will answer the questions in between the talks. So after this presentation, you have the chance to post questions. Sorry about that.
Thank you.
Go on, Jory. Yours the floor back.
Thank you, Naomi. I think we are right on track. So, how will the provider perform demand response then, in order for this overall optimization to lead to a win-win situation, which is both beneficial for the user and the provider? So the provider has to perform his own optimization. For example, it can be maximization of flexibility for a certain budget for DR incentives to be given to users, or he can try to meet a certain flexibility level, a certain reduction of energy consumption with using the minimum budget of for incentives. But he has to do this knowing that each user to be selected for demand response should be offered his own individually optimal incentives. Otherwise, the user would not be adequately compensated and he would not participate. So, for example, if we assume a very simple case where we have several households and each of them can contribute 1 unit of reduction of demand, if adequately incentivized, then the optimal thing for the provider, the optimal approach, is to select those households that require the least incentives for participating in demand response. How many? As many households needed in order to meet the flexibility objective. And this is the so-called optimal DR targeting. Is this a win-win situation? It will be only if the provider's savings or profits due to the success of the DR event exceed the total incentives given to the users. So far, we have only dealt with economic incentives, and we have formulated optimization problem and solved it in a distributed manner using economic mechanisms. However, people are not always purely self-interested. They are not always benefit maximizing or cost minimizing. They don't have stable preferences, or they are not fully informed of their utilities, of how to make optimal decisions, etc. So behavioral economics employs psychological experimentation to develop theories about human decision making, and also provide means for taking into account such behavioral traits in order to perform more efficient, more effective DR events. For example, we can incentivize users who are altruistic or environmentally friendly by announcing that their own behavior will contribute to to lower CO2 emissions, for example, and such users will have improved in our research, but will require lower monetary incentives when they, of course, when they are informed about the positive effect of their behavior in their environment, in the environment. Another way is incentivize users by social competition. For example, introduce challenges for energy efficiency and announce users that are doing better than others, and or gamification. And I will show you an example in a minute. So another also premise of behavioral economics is that users prefer to have a possibility for winning, let's say, 100 euros rather than being awarded for sure €1. So, for example, we have also employed lottery tickets instead of lower monetary incentive amounts, because if the incentives that about which I discussed in the previous slide turned out to be a very low monetary amount, then users may not be interested in taking these incentives and participating in the DR event due to this behavioral premise. In this slide, we see a mobile application developed by Project Charge, which was also awarded an award for these applications. And we see a serious game that incentivizes energy efficient user behaviors of employees in an office building. So its users earn points when, for example, taking the stairs instead of the elevator in his work, or when turning the computer off when leaving his office. And actually this is shown also, is depicted in this tree, by which grows up with additional economically, environmentally and energy efficient achievements of the user. At the same time, there was a competition among teams in order to harness also the social competition incentives. And all these are quite relevant to our project BUILDCHAIN. And this is my pre-final slide. So because in use case 12 of our project, we aim to improve operational energy consumption and efficiency of certain buildings, namely offices, schools, etc. And also to develop and install mechanisms for improving the energy flexibility of buildings. So what should we do? First, we are going to identify the potential for improvement, both of energy efficient user behaviors, that is how the users of the building, namely the employees, the students, and the staff of schools, etc., will be incentivized, and how what potential they have to behave more energy efficiently. And then as we will see in the next slide, how they can be incentivized for this. And also at the same time, we should look at energy-related building characteristics in order to improve, for example, the thermal capacity of buildings by means of improved insulation materials at the innovation phase. And this will provide the building owner a higher potential of participation in DR events and attain DR incentives, which can be beneficial for the building owner as a whole. So we have to identify wasted energy, like for example in off-hour consumption, and reduce it by means of right incentives. And for example, we have to encourage turning off devices when not in use. We have to encourage synergistic usage of common appliances and notify users for participating in VR response events. That is, the building as a whole will participate in VR response events. And how can these incentives be offered? In the way I mentioned in the previous slides, using, for example, the mobile app or some kind of lottery tickets or a movie ticket or some other kind of benefit, provided, of course, that we have the right means of recording that or verifying that such energy behavior efficient energy efficient behavior, sorry, have actually taken place and have been adopted by the users. So thank you very much. Thank you for your attention. I will be happy to answer to questions posed in the Q&A session.
Thank you, George, for this really interesting talk. And let me check the questions and answers. And I see no questions. So you still have time to pose a question until maybe I do pose a question. I think it's a very interesting idea to introduce this gamification into the whole process. But what kind of information do you need for these methods in advance, or how do you know that it's worthwhile to invest in developing an application, and if it's gonna motivate people enough?
Yes, thank you very much, Noemi. This is not one question. I think it's three
Sorry. Sorry.
So let's start take one by one. So you are right that in order for a community, a building, and both of them to be capable of harnessing energy efficient behaviors, we need some kind of investment, like for example sensors, like exchange of information through mobile phones or using some tablets. So there is an investment needed, and of course we have to assess the benefits of a successful running of the application and the efficient and attaining more efficient, more energy efficient behavior, and at the same time compare them to the amount of investment needed in order to install this equipment. So we can have a very successful and demand response participation in several events. We can have very successful induction of energy efficient behavior. But if the investment necessary in order to run the thing is high, then we may not be beneficial. So in such cases, we may let's say sail for simpler simpler investment, and let's say have a less perfect induction of incentives. For example, we can have less recording sensors or less information exchange, but if we can have a beneficial overall case, this might be better than trying for the perfect solution, which would be very costly. So as you also mentioned, there is information needed in order for us to run such applications. For example, we have to identify the possible energy efficient behaviors. We have to pass this information to users. We have to explain to them how these behaviors can help the building and how they can help the environment. And for example, explain to them that they will lead to lower CO2 emissions and why this is important, etc. And also we need information recording or the energy efficient behaviors in order also both to make sure that we make our goals, and at the same time that we pass the right incentives to those users that have actually exhibited this information, this behavior. So this is a very important issue because we have an overall a common goal, but at the same time this goal is met by means of behaviors of multiple individuals. So we have to make sure that we know which individuals were indeed the ones that exhibited the right behavior, and give the information to them and give the incentives to them. So I hope I covered.
Thank you, George, for the really extensive answer. And I think it would be also interesting to see how this BUILDCHAIN system that we developed with the help of decentralized knowledge graph will be integrated with this idea so we can really explore the opportunities of these methods. But this is the topic of further later talks. So we would like to see the next webinar talk by Katja. So let me present you first, Katja. She's an assistant professor. Her name is Katja Malov-Ribet. I try to pronounce correctly her name. She's the head of the Laboratory of Thermal Performance and Acoustics at ZAG, the Slovenian National Building and Civil Engineering Institute. She has a highly interdisciplinary group, and accordingly, they are working with highly interdisciplinary projects and very interesting ones. Her main research interests are energy efficiency of buildings, digitalization of buildings, environmental aspects of buildings. And she has a very interesting special field, which is the non-image forming responses to the lighting and daylight conditions of buildings for the occupants, which I find really interesting. And unfortunately, we won't be able to hear about this today, but we'll hear more about sustainability. But that will be also an interesting topic. So her group is shifting to create a human-centric decarbonized building in the future. And Katja, yours the talk.
Thank you very much. Hi there. Thank you for this beautiful presentation. Okay, I'll share my screen, and there we go. I hope you can see it. So yeah, today we'll talk a bit about how we report the data related to sustainability for the built environment, and how digitalization could actually drive a huge change with that and help us to make better informed decisions, hopefully. And also in the previous talk, there were some keywords already mentioned, like behavioral incentives and also conflicting interests, for example. So let me start maybe from establishing why sustainable data and the whole environmental, let's say, footprints issue can be quite challenging. What we'll do, we will try to explore why are we focused on decarbonization of the building stock, what's the LCA, and then what's the relation between the energy efficiency data, but other use phases, I mean, other phases too, not just the use phase, and the overall picture. And then in the end, we'll look into future and try to answer a little bit about what could future reliable and comparable data sharing look like for the environmental footprints. This time around, I don't know, maybe a little bit later. So we'll just start head on. As you know, like environmental issues can usually sometimes be perceived as maybe exaggerated, or there are also like some fights between what are facts and what are not. And in the end, it sometimes just comes down to putting blame on others, and having that's possible due to not having reliable enough data. So I'll just point out a few things that are with sources, and you maybe know them or not, but the construction sector, for example, is responsible for 23% of air pollution, 40% of drinking water pollution, and 50% of landfill waste worldwide. We, in the building construction sector, account for almost 40% of global carbon dioxide emissions. And also, it was just with the production of construction materials such as concrete, steel, and aluminum, we produce like 11% of global greenhouse gas emissions. And then also, building sector generates like 30% of all waste around the world. Some of it like not so little toxic or hazardous. And also, as you already know, building construction sector can significantly contribute to the soil erosion, loss of biodiversity, and also we just destruct natural habitats and affect ecosystems in a really bad way. So those are kind of maybe, let's say, why look into this topic more thoroughly. And now maybe some main ideas what we are focusing on. So first of all, we are quite worried about the climate change, since, as I previously mentioned, buildings are one of the major contributors to the greenhouse gas emissions, not just in the use phase, but also on the stage when we are still designing them and constructing them. This can be a huge challenge. Next one is resource depletion. So by building buildings or just built environment in general, we consume significant amounts of natural resources, energy, but also water and materials. So this might not be good for our future generations, and we might want to take a look into it and maybe change some of our practices. Also, we are kind of focused on energy efficiency, so we might want to reduce the amount of energy we need to power our buildings due to a huge demand of fossil fuels, for example, related to this topic, and also other issues that are the resulting. And then, of course, health and well-being. We try to provide better indoor air quality, for example, also natural lighting, daylight, improve thermal comfort, and so on. But we should do all of this in a balanced and informed way, so our human needs are met, but also the environment still can function further, and the occupants of the future will also have similar opportunities that we have. And then maybe also to mention main ideas related to the decarbonization of building stock should also be related to regulatory requirements. So as you know, many countries and regions are implementing regulation and standards to encourage sustainable and decarbonized buildings, but those should be like, let's say, a team effort stunts. So it's not enough if only a few are pushing in one direction and the rest are not participating. So that would be for the first question, and then let's move on to more practical part, life cycle assessment. Many of you have heard of it already. Some have maybe even some experience, but in my experience, most of people are just like, oh, that's something complicated and not so reliable, and yeah, whatever. It's actually a method that's not that new. It's been developed quite some time ago. And with the LCA, we try to evaluate with numbers environmental impacts of products or systems or the whole buildings or districts throughout the entire life cycle. So from the point where we extract raw material by the end of the life cycle, which is disposal usually. Now, here are the major stages of life cycle broken down into what we call these modules. So we are saying here in the A module, we are talking about production stage. So here we evaluate all the environmental impacts that will be the result of, so let's say, raw material supply, and then transport and production of a product or multiple products or services. And then this other part, the construction part, relates to the transport to the gate and the assembly. And then for the use stage, here we are talking about the all the environmental footprints that will be made during the use phase, during the maintenance, repair, replacements, refurbishment, and also very relevant and like most talk about operational energy use and also operational water use. Those are all the things that we are trying to account for in the use stage. And then end of life stage, EO stage, where we are trying to account for all the deconstruction, demolition, footprints, transport, waste processing, and just disposal. And then we are also capable of reporting in the LCA a D module, which is reuse, recovery, recycling potential. So kind of a benefits beyond the boundary of the system we are working on. So these are maybe the main phases to remember. And for sure, they were also incorporated in standards, as were also other things. So we are working with at least three very much important standards. The first one is the about just the basic framework of the LCA. Then the next one, we introduced the goals and the scope, definition, inventory analysis, and impact assessment, and also interpretation. So this is these four main phases of LCA. And then the last one mentioned here, not the last one, the third one mentioned here, which is also EN, so European standard, it's 15804. That's a standard that provides a common framework for reporting what the construction products and materials life cycle assessment should look like. So this is the basis for the documents, EPDs, which we will mention later on too. Here I mentioned also two other approaches. So those are not the internationally approved standards, but still there are also other ways, or people are working on different approaches on how LCA could be conducted, or at least parts of it could be integrated in as big as a possible population. So this is one example of the results of LCA, very much loved results. No, they are quite complex usually and demand a good interpretation. So here you can see the parameters on the left side, which I will explain, and these are just comparisons of the outcomes for bricks and windows, lamps, and air handling units. Just like to see one example of the results on the flight. And now what the impacts, the indicators we are calculating are, there's many of them, and this is not the whole list. I will just maybe mention a few that are more talked about. So we talk a lot about, we are worried about green gas emissions. So one of them being CO2, that's why decarbonization, but there are also others that are important. And how we report this global warming potential in terms of CO2 equivalents. And we report then separately also global warming potential for the fossil fuels and the biogenic part. That's because there is a tricky part in LCA methodology that we call sequestration, where materials like wood are treated as materials that can actually store CO2. Usually we calculate LCA for 100 years, and wood, it can be used, especially if we use it in cascade manner, for longer than that. So we kind of say that when the trees are growing, they suck the CO2 out of the air, and then it's stored biogenically. And that's why we see that as a material that might be environmentally, let's say, positive. Then we are also looking into two types of ozone. So there's a depletion of stratospheric ozone, which we don't want. We want to have this layer to protect us, but also there's a ozone that is forming here, potential of tropospheric ozone. So there's the ozone that is formed near the floor, and that is like harmful to like lungs of people, but also harms materials and so on. Then we are worried about acidification. So where we have these exceeding accumulated acids, and also eutrophication, that's nutrition, like excess nutrients in different waters. So we are assessing separately freshwater, marine water, and so on. And then we also, part of like standard LCA is also abiotic depletion potential for separately non-fossil resources, and also for the fossil resources potential. And for sure, we are also assessing water deprivation potential or water total use, or just different kinds of environmental aspects for the water. So that's on the fly, just to know what you can expect as a result out of the LCA. Now, to report that, I've mentioned before, we have this standardized way of reporting it, named Environmental Product Declaration, which is a few papers thin report, where it's based on the international standard, and also so the operators, the program operators that can issue this EPD are being regularly checked among each other, and are part of the network, a global network that is collaborating and trying to establish mutual rules, which is helping with the integrity and also the, let's say, reliability of data immensely. Now, what are the main problems of LCA? I will go one by one, but let's mention them first. So first one, complexity. Time frame can be challenging, boundaries, establishing what will be in and what not, interpretation, costs, and for sure, data availability. Now, for the complexity, probably that's, at least you've heard about this one. So as you know, it can be very complex to approach LCA, especially for bigger systems. So here we need to always make some model and assumptions and scenarios, and this is one of the things that then people might just dismiss the results as irrelevant due to the complexity not being addressed in a proper manner. Then the time frame that's related to, so the time frame, buildings being like, you know, having this long lifespan, so that could be like spanning several decades, and it means that what we are calculating now might change in future, and that the more in future the data occurs, the less reliable it is in average. Then the boundaries, so for example, what to include and what not to include in the assessment, for example, like with the building the buildings, how to include the infrastructure needed, or for example, that's famous thing about the electricity footprint, the kilowatt hour footprint in countries. So should we also include infrastructure like electric lines, transformers, wires, and towers? Then for sure, one of the problems is interpretation. Results can be difficult to interpret, and even when data is collected and analyzed, it can be challenging to determine how to prioritize really various aspects, namely like for sure global and then local, but also other aspects. And this interpretation makes LCA a little less objective that we would hope for. And with developing good standards, in depth, also like category, we call those category rules, we can actually overcome this issue and make the interpretations like similar one to another, and therefore more reliable. And then cost. For performing LCA is time consuming and costly, and especially in the past, this was quite a quite a problem for the industry, but I think now with more and more data being available and also openly being available, this is becoming less of an issue. Now, since we are with the data availability, so collecting the data for these various components, materials, and processes can be very challenging. This is usually not just the thing about the one who actually performs the LCA, but we also need to get the good data from the manufacturers, for example, that might be or not interested in cooperating, which can be challenging. And a separate problem for sure that maybe it's not so much talked about, but it should be, is that we have these big data collections, but they are proprietary. So yeah, the thing is that the scientific papers are on the other hand open, at least some of them. And there the results are not reported usually in a standardized manner. So this can, this issue can be quite, yeah, challenging for to get the good results in the end. So as you know, we have this cascade use of the data in the LCA, so we don't just calculate everything from the ground up, and that's why it's so important to have this good data, reliable data, and for sure, if it would be like open source, like open to everyone, that would be the greatest option. Now, for the energy efficiency part, so the use phase and how it affects the overall picture. So I'll just show you a quick example where we have bricks and lamps. So life cycle assessment for the brick, for example, has this biggest red part in the production stage. But the lamps, for example, have like only like 25 or something % of the environmental footprints located in the production stage, and all rest is actually the use stage. For sure, we are using energy with them. And this is the thing that can be challenging with assessing overall buildings or even like long-term development of whole building districts. Because here you need to have reliable models that will take into account different life stages as they occur. And as I said before, the further away from, like in the future they are located, the less reliable data we can work with. It's a bit similar like with money.
Katja, you only have a few minutes.
Thank you. I will be very quick. So maybe just to mention end of life phase, there's for sure potential also, especially or also for the building stock, to apply these principles of circularity and to extend service life, to reuse, recycle, then do things before disposal. And those can even be accounted for in the LCA, although it's, again, a complex thing to do. Now, for the end, we would like to say something about the data sharing and make it comparable and reliable, for sure. So, you know, the scientists and atoms and how the atoms like to share, but scientists are kind of, you know, not so, they don't trust the atoms so much, since the, you know, this concept of atoms making up everything. Anyway, I promised to joke. I will quickly do the rest. So the data analytics could help immensely with sustainability data. Like, for example, we could integrate it in platforms and use machine learning algorithms to identify patterns and trends, and then just also identify opportunities for us to optimize building sustainability performance. Then material passports should be mentioned. These are the documents that provide information about materials used, so you can here have you could have a better decision-making tools for material selection, and based on that, design of future buildings. I've mentioned already certification programs. I've mentioned EPDs, but those can also be integrated in bigger schemes for certification of the whole buildings, like LEED, BREEAM, WELL, or there are also others. So with that, this could also be one of the incentivizers to take into account environmental and sustainability aspects. And then the last thing, but probably the most important, is the digital logbooks. So we could track the building's performance over time and include energy and water consumption, maintenance, repair plans, and so on, and all these activities and upgrades. And by integrating such data, we could track the environmental impact in the building over time. And this information could be used to identify opportunities. And ultimately, by sharing data, we could also help like with entire districts or cities to become more sustainable. So I believe I've covered everything I've promised. And now for, ask me anything session, are there any questions?
Actually, there are questions, Katja. And I will pause them just in a second. I just wanted to notice that there was a question from for George in the questions and answers section. So if we will have time at the end of this webinar talks, we will have some time that George can answer in live to your questions. But until then, can I ask you, George, just to drop a short answer to this question in the question and answer section, and after that, Katja, you have a question by Jenny. So first of all, it's mentioned that your presentation was very informative, and the question is regarding the LCA databases. How about data from the open databases like Okenbudat? I don't know how to pronounce that one. Maybe you know better.
Equitable. That's a German LCA open database.
Are they good for use? That's a very important question. I think we even had a discussion about this.
So do I answer now?
Please.
Okay, yeah. About that is great, and it's been formed like it's not that young anymore. So they are continuously updating it, which is great. Germans put like a lot of money into establishing that many years ago, and it's great. But there are like many specific data that are like country specific. Like for example, mentioned before, kilowatt hour for Slovenia, it's quite different. We have our own mix where we are, for example, we have this nuclear power and so on, and this should be reflected in the LCA for sure. And there are also other country-specific things that, so if you work with German data for Slovenian cases, you will for sure have a certain percentage of mistake. That's one thing, but the thing is that like not all the countries have such a database like about that. So we know that people are using data also from databases like that. And that's why it's so important to have some means of checking LCA also by someone else, and not just having the people that do the LCA, and that's the final step. Then another question is regarding the interpretation of the results. So what would be a good way for comparing, let's say, individual house? That's a cool question, because the main idea of the LCA, at least at the beginning, was that we would just like to calculate what are the footprints of different products and services and so on. So we didn't want to focus on comparisons between, let's say, similar or even same products. And this was also the idea behind the EPDs in the beginning. But as the market is developing, we see more and more now of these attempts to make comparisons, which can be very, very demanding, and also it can be skewed, and the whole point is missed in the end. Because usually you need to assess your problem, which is for sure multi-parametric, taking into account the things that are really there. And that's why like with the buildings, you usually don't have two similar buildings. That's why it's so important to have this case-by-case approach and not focus on comparing to the others, but more comparing to yourself, or what is the best option that you can pick from the solutions that are available to you in terms of environmental aspects. And there's another question for Katja. What about
Katja,
database? Sorry,
Katja, let's do that afterwards. Okay, you can. Okay. Maybe great. You can answer written, okay? You can type the answer, and then we can get back to it at the end of the webinar talk, because maybe some people have to go. So let's leave the floor now to the next. So thank you, Katja, for the great presentation.
Thank you. I would also like just to mention that there's a huge team working on this. It's not just me. So here with me today is also Patricia, and I think Lisson is also listening, but there are also other people that have contributed very much to this presentation. Thank you. Thanks,
Katja. So let me introduce you now to Enrico Scodetti. He's a building and architectural engineer at RINA. He has a broad experience in, oops, just a second. Okay, it was Zoom somehow changing my window because the unshared window. Okay, so he has a broad experience in site supervision and safety coordination. He's mainly focused on energy analysis of building envelopes and economic and financial assessment of real estate investments. And he has several such projects at RINA, and he's also collaborating in EU projects such as this BUILDCHAIN project. So please, Enrico, yours the floor.
Thank you very much. I'm going to share my screen. In order to provide an idea of what, thank you for the presentation, Noemi, first of all. And in order to provide an idea of what a techno-economical assessment tool is, I'm going to present the TIA tool developed in the context of other European project where RINA Consulting is involved as our partner, and that we are going to further develop in the context of BUILDCHAIN. The TIA tool is intended to provide support at the very preliminary stage within housing renovation projects by enabling the comparison of different scenarios through an automated and simplified user-friendly process. It provides preliminary guidance and information in terms of cost, waste generated, but above all, user disruption. Our tool focuses primarily on the assessment of user disturbance, which is often overlooked in the context of housing renovations. Renovations projects typically disturb building occupants and vice versa. While planning and executing retrofitting activities, project managers must consider occupants' presence and schedules so they can adapt accordingly the construction site pathways. When occupants are present in the renovation site, disruption due to noise, dust, vibration, odor, and demolition debris should be reduced as much as possible. The cost of renovation project should include the added cost caused by disruptions, so as to enable the project manager to evaluate and compare different retrofitting scenarios and decide about the best retrofitting strategy to be implemented. To emphasize this aspect, emphasize the fact that of a non-negligible nature of this cost, it should be mentioned that research studies suggest that disruption can increase cost by up to 12%. In other words, user disruption and related costs are aspects that need to be kept in mind from the very early planning stage. The two main strategies to manage and reduce the impact of disruption during renovation projects have been proposed in literature. First, communication with occupants to explain the renovation process, build trust, and minimize the impact of disruption. Second, enabling renovation scenarios assessment, simulation, and optimization to minimize user comfort, to maximize user comfort and minimize disruption. The TIA, the techno-economic assessment framework, was developed in order to implement these two strategies and enable project managers to efficiently communicate, evaluate, and simulate renovation scenarios to select the optimum one with minimum disruption that could be caused by two occupants. In addition, the T framework permits the evaluation of renovation project parameters such as project duration, cost, and worker needed during the renovation works. The techno-economic assessment framework include three main components, which are namely a renovation ontology and its database. Second, the T tool along with a friendly graphical user interface to enable automated renovation scenarios, selection and evaluation, and the T KPIs to enable renovation strategies, comparison, and optimization. These slides illustrates a general overview of an automated process implemented through the techno-economical assessment tool. It begins by importing a BIM model and then allowing users to define renovation scenarios to be simulated. Secondly, based on the renovation ontology and the related database, which will be described in the following slides, the T tool maps the renovation scenario to corresponding activities and relevant equipment. Thirdly, building elements and material quantities are generated from BIM models and linked to the renovation activities, which allows the generation of a renovation schedule corresponding to the scenario selected. Finally, using the database developed, the TIA tool estimates and simulates disruption levels. In addition to cash needs, etc., etc. Here, however, to develop the techno-economic assessment framework, first of all, a renovation ontology has been proposed and validated. These slides introduce the defined renovation ontology through a new ML class diagram illustrating the basic concept, the relations and constraints, as well as the attributes that define each concept to facilitate its implementation and population as a renovation database. As shown, a built asset is composed of several elements such as windows, wall, HVAC systems, etc., and many areas. An element could be manipulated while achieving a renovation scenario. A renovation scenario takes place at one or many areas, manipulate one or many elements, and could involve the installation of many innovative products. Each renovation activity is timely constrained by activities that should begin and finish before it, while some others will be triggered and executed after its completion. It also requires a set of material, workflows, and equipment to be carried out, and it may cause disruption to the building occupant. Only 4 types of disruption are considered so far, namely disruption of traffic, utilities, physical space, and internal environment. The renovation ontology proposed was populated into a database, which included several tables, each one allowing the implementation of a concept from the ontology. Data related to renovation activities, their sequencing rules, constraints, duration, cost equipment, disruption, and waste were all gathered, structured, and validated. This slide presents the main renovation activities identified so far for the TIA tool. They are just only 20 activities coded from A to T, named and detailed in terms of sub-activities and procedures to be executed during renovation project. Two existing levels of sequencing rules were identified between renovation activities, namely spatial rules such as courtyard related activities, for instance, site preparation must begin first, and then another group of rules that are the activity-based rules. These slides show the diagram of spatial rules adopted for the definition of automated work schedule. The activity considered at the same working area are also timely ordered. Some activities should start first, some should be scheduled at the end. Others could be synchronized and done simultaneously, while others must be disjunctive and cannot be conducted at the same time. To provide an example of the activity-based rule considered, these slides present the renovation activities that could be conducted in each working area of a renovation project and indicates their usual sequential order. For example, a terrace is renovated by starting with activity F that I don't remember what is, then activity L, and final activity I. As said, only 4 types of disruption have been considered, namely the disruption of traffic, interruption of utilities, physical space, and internal environment. As shown in the table at the bottom right, some level of disruption are considered as part of the normal operation of building, whereas some other could significantly impact the entire renovation project and its benefit. The survey conducted so far enabled to characterize each type of disruption and quantify its levels. As for the 20 renovation activities and their sub-activities. Furthermore, each activity is characterized in terms of duration, cost, and number of workers. The actual estimation were made have been standardized and were made simplified. The actual estimation have been simplified, standardized, and made at the levels of sub-activities, and then average values for each parameter were calculated. The diagram at the top right illustrates an example for an activity and how these average values have been computed, while the table on the left shows the summary of results for the 20 activities that populated the database so far. Here, the practical steps where the T tool has been demonstrated using a real case study are described. The first step in using the T tool consists in uploading the BIM model within the BIM authoring platform. Here we're using Autodesk Revit to enable data preparation, data control, and inputting basic renovation project information. The BIM model should comply with some, for instance, simple modeling rules. For instance, the BIM model should be created with respect to a story-based modeling approach. This means a BIM element should belong to only one level. A wall object, for example, should not link more than 2 levels. The second step consists in defining a renovation scenario that will be simulated in order to estimate disruption caused to user and waste generated. The TIA tool provides 3 different graphical user interface to enable users to create their own scenarios and simulate them automatically. The first graphical user interface allows users to select the areas that will be renovated, as well as imputing data related to the number of apartments existing at each level to be renovated. The second graphical user interface enables user to define their scenarios by selecting renovation activities to be performed for each area. The third graphical user interface provide a list of renovation equipment so as the user can select some of them to be used for renovation activities. The last step consists in estimating the different types of disruption using the schedule generated, and finally using the techno-economic assessment framework, the different renovation scenario can be evaluated according to their cost, duration, workers needed, and disruption caused. In conclusion, a brief overview of the benefits brought by this tool. It allows a quick estimation of the renovation project duration, the waste creation, and above all, provide a way to quantify user disruption during renovation projects. About its limits and further development, there is obviously a need to expand the database of activities considered, which is currently limited to 20 activities that were the ones needed for in the context of a European project that has been developed. And there is a need to develop the tool so that it works more flexibly and accurately, even on complex projects. And that all for my part.
Thank you, Enrico. So it's time for questions. You didn't receive any questions in the in the question and answer section. So I will just ask a short question. So this, if I understand well, this tool can be used by anyone. It's open source. So, or did I misunderstand that?
Yes, but we are. Question is for me. Sorry.
Yes, for you, Enrico,
okay.
of course.
Yes, it's going to be open source. Not now is just now is plugin for Revit, but it's going to be have to be an open source.
Okay, great. And do you plan to extend it the way you described in the summary section within this BUILDCHAIN project, or is that in the plan or not?
No, we plan to extend the tool in the context of BUILDCHAIN.
Mm-hmm.
Obviously, we need to because now is we developed this tool from scratch. Now is not have necessary flexibility. We expect it has to have for this kind to analyze different situations. Is extremely simplified. We need to complicate the tools and make it more flexible.
Thanks, Enrico. Thanks for introducing us to this interesting tool. And before we stop recording, I would like to ask George if you could answer this question that we received just meanwhile you answered my question, sorry. They asked, sorry, it was Lyubomir who asked how many installations and companies use this method that you presented.
Thank you, Noemi. I'm not sure, and thank you, Lyubomir, for the question. I'm not sure if it refers particularly to the application of project charts that I presented in my presentation. This is what I guess looking at the time when the question was input. So this application was trialed in the building of the municipality of Athens for some time, but I don't think it was, let's say, adopted in the production, let's say, operation of the building. So in general, there are other projects as well which have developed energy efficiency applications to encourage such behaviors, but I guess their use in the real environments by real employees is limited. But I can point the audience to another very nice example, which concerns the subway station in Stockholm and the so-called piano stairs. There's a very nice video in YouTube where you can see that there's an installation of sensors and other equipment so that if a passenger takes the stairs rather than escalator or elevator, then music is played by his steps. So and this can be considered, let's say, as a serious game with giving some individual incentive for a person to exhibit an energy efficient behavior.
Nice idea. We just started this webinar by thinking about playing some music, right, Katya?
So subway station in Stockholm, piano stairs. If you write this in YouTube, then you can see this very nice video.
Thank you, George. So I would like to close the official part of the webinar here, but I invite everyone to stay in the Zoom platform, and you will have a chance to switch on your microphones and ask real-life questions if you would like to. Maybe Katya can also answer in word to Yelena's question. But we will stop the recording here, and thank you for the attendance.